The way that this works is that you have your current class loader that contains the current version of the classes in your application. For example, I have this simple offset class here with just a single property in it. And when you receive new bytecode and you want to load the new version of classes into the app, those classes will be loaded into a side universe class loader. All of the existing instances of offset, in this case, that are already in memory, will be migrated from the old version to the new version. And once that's done, the side universe class loader simply becomes the primary class loader, and the execution of your application continues from there. Let me show you a more visual example of what that migrating part actually looks like, because it's not trivial that we can take existing objects that are already in memory and we can change their structure. So how do we do that with DCVM? Again, let's stick with this example of an offset class, and let's say that we have a couple of instances of it already in memory. So we can imagine that these would sit somewhere in the heap. They would all have the object header that every object on the JVM has, and they would also have the space in memory where they store their actual values. Because we're storing just a primitive int here, it would be the actual value of the int that's stored there in memory. In order to add a new field to this class, we'll need to allocate new memory for each of these instances. So we'll go ahead and allocate some new memory for each of those offsets that are already in the memory. And for the fields that already existed, as well as the header of the class, we can simply copy the existing values over to the new space that we allocated. And then we'll have the space that is the make space for the new property that we added, that y property up there. And new properties like this, we just have to initialize to some kind of value. And the way that we do this is that we use the JVM defaults in this case. So for numerical types, these would be just zeros. For reference types, we would have to initialize them to nulls. For booleans, it would be false, and so on. And once we have these new versions of each of the offset objects, we can simply drop the old versions and continue executing the code from here. If you think about it, what we're doing in this case is basically a special garbage collection pass, because we're pausing the application for a very brief moment. We're moving some existing objects to new locations within the memory, and then we can resume executing the app. So we're kind of just performing a garbage collection here, but we are also changing the structure of classes potentially as that's happening. So once we have all of the classes changed and the bodies of functions reloaded across the old and the new version, as you have made your code changes, we also need to invalidate some of the Compose UI, as I mentioned. So for this, we need to do some intelligent diffing of which part of the Compose code has changed exactly. For this, we maintain complex structures in the background, and I'll reference a talk at the end of this one that you can check out if you want to learn the details of that. But essentially, we keep track of the contents of every group and every function that's used in your Compose code, and we can detect changes in the bytecode of each of those different composable groups.